Very good morning to all. This video lecture going on Cayley theorem in graph theory. Okay. First, we see that labeled graph. What is labeled graph? A graph in which each vertex is assigned a unique name or label is called a labeled graph. Okay. A graph with n vertices. Each vertex has distinct name like v1, v2, v3, etc. Doesn't matter, but distinct name. Suppose first one is v1, the another one is v2, another one vertex is v3, and going on, but not two vertices in same name is called a labeled graph. Understand? Next, state and prove Cayley theorem. What is Cayley theorem? Statement: the number of labeled tree with n vertices n greater than or equal to 2 is n power n minus 2. So let the number of labeled tree. What is tree? Already we know that tree is a graph without circuit is called tree. Okay. Labeled tree is a graph without circuit, and also the name, the each vertex have name, the name are distinct. Okay. N vertices, n greater than or equal to 2. At least two vertices have, a graph have at least two vertices. So is clearly out, no isolated tree. Okay. Is n power n minus 2. That's only Cayley theorem. Okay. Next. Let the number of vertices of a labeled tree capital T be n. Okay. A given labeled tree, number of vertices in n. Okay. First, you draw the sample tree capital T. This T have 9 vertices, right? First level is 1. This is a rooted tree. First level is 1, second level 2, 3, 4, third level 5, fourth level 6, 7, 8, and fifth level 9. So this tree are got 5 level. Okay. First of all, the tree have 9 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9. Given vertices are, note that first. Then every tree have center of vertices. Already you know that. What is center of vertices? You remove the all pendant vertices, you get in center vertices. The center of vertices, one or maybe two vertices are center. First you remove the pendant vertices of H. First you remove pendant vertices also, you know that the single vertex assigned with another vertex. Okay. This is a single vertex. This is called a pendant vertex. Okay. First you remove that first pendant vertex is 4 and 2. So 4 and 2. 4 remove the vertices 1, right? 1. At the 2 remove the pendant vertices also assigned with the 1. Okay. Next 4, 2. Next pendant vertices you got 1, 3 1 3 5 8 6 7 and 9, right? Next pendant vertices 1 assigned with 3 up, so 1 is removed, assigned with 3 have also 3. Next pendant vertices, this is cancelled. Next pendant vertices are 3 and 5. 3 is cancelled, 5 are there. Okay. Next pendant vertices 5. 5 to 6, 7, 8. 6, 7 are pendant vertices to 5. So 6 combined with 5. Next 7 combined with 5. Next pendant vertices is 5, 8. Next you have 5, 8, 9. 5, 8, 9. This only. The pendant vertices are 8, 5 and 9. First cancel 5, 8 have. Okay. Next 9, 8 have. So all pendant vertices you remove 1, 1, 3, 5, 5, 5, 8. You have the vertices. Okay. Total 9 vertices, but remove the pendant vertices. You have 1, 1, 3, 3. How many digit? First 9 digit. How many digit? 3, 6, 7 digit. 9 digit and 7 digit. So 9 element and 7 element. N power n minus 2. You apply n is 9. 9 power 9 minus 2 equal to 9 power 7. You got that. Each labeled tree have n into n minus 2 elements. Whatever it is, which tree you have, which labeled tree you have n power n minus 2 is called Cayley theorem. Thus, next we say that the reverse process, the first sequence and the second sequence, the numbers does not appears, the numbers of first sequence does not appears in second sequence, then constructed tree with us. First, the first sequence number 1 same is second sequence. Okay. Next is number 2 does not appears in second sequence, so get number 2 from 1 and 2. From 1 and 2 you construct first tree H, 1 and 2. Okay. Then 3 you have second sequence, so does not appears. Fourth one is that's appears, 3 that appears, so fourth is does not appears. Then we construct 4 in 1 to construct another agent on tree. Next 2 cancel, in 1 cancel. Next 4, then 1 cancel. Next 1 does not appears in sequence 2. Why? 1 are already cancelled, so 1 does not appears in sequence 2. So 1, 2, 3 that edges are constructed. You understand? That edges are constructed. Next 1 and 3 are constructed. Next 3 does not appears in second sequence. So 3 constructed with 5. 3 constructed with 5. 3 constructed with 5. Then you cancel 3 and 5. Next 5 appears on second sequence 5. So does not get. Next 6 does not appears in second sequence. So we get 6 constructed with 5. 6 constructed with 5. So 6 and 5 cancel. Next 5 appears in 5. So does not get. Next 7 does not appears in second sequence. So 7 and 5 we get. Okay. Plus 7 another edge construct with 5. This is 7. Okay. Next 5 are cancelled, 7 are cancelled. Next 5 does not appears in second sequence. So next 5 to 8. 5 to 8 we get. 5 to 8 on edge. Next 8 and 9 only have remaining. So 8 and 9 you constructed edge. Again you get the same tree. Okay. Now this process are say in proof clearly out in written format. This concept are same as this written format on there. Okay. Listen. Let vertices be labeled by 1, 2, etc. n respectively. Let us remove pendant vertex having the smallest label with the edge incident on it. Let this pendant vertex be A1 and B. Let B1 be the vertex adjacent to A1, and let us remove the edge A1, B1. Already we say that suppose 1 is A1, 2 is B1. Suppose 1 is A1, 2 is B1. Okay. In general case, so only have this tree 9 vertices, but the general case n vertices tree A1 and B1. Remove the pendant vertices. The smallest label edge incident with on it. Let this pendant vertex be A1 and let B1 be the vertices adjacent to. Let B1 be the adjacent to A1 and let us remove the edges A1, B1. Okay. Already we see that. The same process on general case. Among remaining 1 pendant vertices are removed. Remaining n minus 1 we get vertices. Let A2 be the another vertex. A2 be the another vertex. Again the process repeat the pendant vertex with the smallest label and let B2 be this process. Among remaining n minus 1 vertices, let A2 be the another pendant vertex with the smallest label and let B2 be the vertex adjacent to A2. Now remove the edge A2, B2. This process is repeated on remaining n minus 2 vertices and then n minus 3 vertices and so on. Next, if pendant vertices A2 A2 and P2. Okay, you remove again the pendant vertices, we get n minus 2 vertices. Then again you remove pendant vertices, you get n minus 3 vertices, and so on. Okay, next the process is terminated after n minus 2 steps when only 2 vertices are left. The process are continually in end only 2 vertices are left. In this process we get a sequence b1 b2 up to etc pn minus 2. Already we know that b1 p2 up to etc pn minus 1 sequence we get the sequence 1, this sequence 1. Next, in the converse way, with the help of sequence in 1, the same tree may be constructed as we have n labeled vertices and we have make another sequence. The another sequence are first sequence is sequence 2. Next, now let us determine first member in sequence 2 which does not appears in sequence 1. Its member is clearly A1. Now H A1 B1 is constructed. Already we see that the reconstructed diagram, first sequence does not appears in second sequence, then you constructed H1 tree. The same procedure on written format. Now let us determine first member in sequence 2. Sequence 2 is that's 1, sequence 2, sequence 1. So sequence 2 which does not appears in sequence 1, its member is clearly A1. Now edges A1 B1 is constructed. So 2 does not appears in sequence 1, sequence 2 does not appears in sequence O. First constructed 1 and 2, this line first constructed, that is or say A1 and B1. Next we remove B1 from sequence 1 and A1 from sequence 2. In the remaining sequence of 2, let us find the first member that does not appears in remaining sequence of 1. This would be A2 and thus H A2 B2 is constructed. It's nothing but the another vertex does not appears in sequence 1. So 4 does not appears in sequence 1. So again A2 constructed with the A1. 4 constructed with the A1 already we see that. That only this process. Now we remove the B1 sequence 1, the sequence 1 and A1 from sequence 2. Okay, A2 B2 are constructed, the next line are constructed, already see that. The same process, this construction is continued till the sequence 1 has no element left. This process continued has no element left. You reconstructed the tree. You already see that in example. Finally, last two vertices are joined. Last two vertices are joined. You recall the video. Finally, you get only 8 and 9. So, last 8 and 9 you constructed in tree. That's only say. Finally, last two vertices are joined. As a sequence 1 is unique for the given particular labeled tree. Next. Next, number of possible sequence denote number of possible labeled trees. It is obvious that any element of sequence 2 can be repeated by some or n minus 2 times 2 from the sequence like 1. Number of possible sequence equal to n cross up to etc. n minus 2 times. Why n minus 1, n minus 2 times? You see that finally you get 2 element remaining. Otherwise are cancelled. Only 2 element are remaining. So n minus 2 elements are remaining. This procedure continually in n minus 2 elements. Okay, that's why say n cross n2 up to etc. n minus 2 times, remaining 2 times. Which graph you get? But n minus 2 times you remove the your procedure. Then n cross up to etc. n minus 2 times. That's also say n power n minus 2, the number of labeled tree. Hence, there will be n power n minus 2 possible labeled trees with n minus n vertices. With n vertices. Hence, proved. Thank you.